I would like to work an example of what's known as a related rates problem. At the end of this video, we will write down a procedure that will help us solve any such problem. In this example, a spherical balloon is being inflated. The radius is growing at a rate of 0.1 centimeters per second. At what rate is the volume increasing at the moment when the radius is 10 centimeters? So I have a spherical balloon, which is probably just a nice assumption we're making to make the problem easier. Most balloons aren't perfect spheres, but this one is, and we'll pretend that's a spherical balloon. I'm going to call the radius r. And what I realize right away is the radius is growing at a rate of 0.1 centimeters per second, so this balloon is changing size. So the radius isn't fixed, right? The radius is changing. And we're asked to find the rate at which the volume is increasing at a particular moment in time when the radius of the balloon is 10 centimeters. So the balloon is changing size, and at this one moment in time, the radius is exactly 10 centimeters. I want to know the rate of change of volume in that moment. Okay, so I need some way of relating the two rates, right? I need a way to relate the rate of change of volume to the rate of change of the radius. And right away, I keep saying rate of change. I'm thinking that we're going to have to use derivatives. Well, I don't know the formula to relate those rates right away, but I do know the relationship between radius and volume when it comes to a sphere. In a sphere, the volume is equal to 4/3 pi r cubed. So anytime I know a radius, I could find a volume. And this is kind of the big concept. This equation relates volume and radius. I need to relate the rate of change of volume. Well, the rate of change of volume would be dv dt, the derivative of volume with respect to time. So that's the rate of change. That's what derivatives do. That's what I'm looking for in this problem. And then the rate of change of radius I'm given, I'd call that dr dt, right? The derivative of radius with respect to time. And the biggest thing here is that in this equation, the volume and radius are both changing. They're both functions on time. So I know this one, I'm looking for that one. So what I think we should do is take this equation and take a derivative. Take a derivative of both sides with respect to time, treating both volume and radius as functions on time because they're changing, right? As time moves on, the balloon keeps getting bigger. All right, so let's take our derivatives, treating volume and radius as functions on time. The derivative of volume is then dv dt, which would have to be equal to, and on this side, I'm going to use the power rule and the chain rule. So 4/3 pi is a constant, so I'll multiply that 3 down. I'll get 4 pi r squared, and because r is a function on time, the chain rule tells me that I need to multiply that by dr dt. This is my formula that relates the two rates I care about, the rate of change of radius and the rate of change of volume. I'm looking for a dv dt at one moment in time where I know the radius is 10 centimeters. So at that moment in time, dv dt would be equal to, I need to plug 10 in for the radius, that's what tells me one moment in time, and then dr dt is 0.1. All right, that's 100 times 0.1 is 10 times 4, I get 40 pi. If I think about my units, this is supposed to be a rate of change of volume with respect to time. That would be cubic centimeters per second. If I look at this equation, I square r, that would give me centimeters squared. And then the rate of change of radius is centimeters per second. So square centimeters times centimeters per second would be cubic centimeters per second. And I have the rate of change I was after. If I wanted a decimal approximation, 40 pi is 125.7 to 1 decimal place, cubic centimeters per second. And if I really wanted to give you the best final answer I could for this problem, I should write it down in a complete sentence that addresses the context of the problem. At the moment when the radius is 10 centimeters, the rate of change of volume is about 125.7 cubic centimeters per second. When you're doing a related rates problem, I do think it's always best to write down your final answer in a complete sentence that does address the moment in time and the whole context of the problem. And it's super important to get the units right, because the units really tell us what's going on. So what I'd like to do now is write down the procedure I was thinking about the whole way through this problem. So as I'm thinking about how I solved that problem, the first thing I had to do was kind of understand what's going on. So sometimes we draw a picture. I drew a balloon. The balloon didn't matter. The sphere part might have helped me. But what I really need to make sure I do in every problem, I need to name the variables and constants. And I wasn't very creative in that last problem, but I called the radius R and I called the volume V. And I had to remember that those were changing as time moved on. So I want to draw a picture and name the variables and constants. 2, I want to write down the given information. And as I'm writing down that given information, I want to make sure I'm always using correct notation. As I think about the problem we just worked through, I drew a picture and I decided to call the volume V and the radius R. And then when I wrote down the given information, I was looking for dV dt and I had dr dt. That's what I was given. And so when I wrote down the information about dr dt, I want to make sure that I wrote it down as a derivative using correct notation. After I have that, I have to find an equation that relates the variables. In the example we just did together, that's where I wrote volume is equal to 4/3 pi r cubed. Some problems might not be that easy. We might have to create a formula. We might have to combine one or more formulas to get what we need, but we will have to have a formula. After we have that formula, we differentiate implicitly. Treating all of the variables as functions on time. Right, when I looked at the formula, volume equals 4/3 pi r cubed, volume and radius were both changing. So I needed to treat them as if they were changing, as if they were functions with respect to time. I'll differentiate implicitly with respect to time and get a formula that then relates my rates. I want to make it a point to point out that we always want to treat the variables as functions on time unless we're told they're constant. If we're told one of them is constant, then we know its rate of change is 0. So we could just differentiate it using the constant rule. If we're not told it's constant, we have to assume it's changing. Finally, after we have our derivative, we can evaluate and state a final answer. If you're looking at the procedure in their textbook, your author does this in 6 steps. When I think about writing down the given information, I always write down what I'm asked to find in that step. He splits that apart into 2 steps. But all in all, the same procedure that I've written here you'll find on page 192 of the textbook. In the next several videos, we'll just do a bunch of examples of solving related rates problems.